Thank you very much. As usual, it's a pleasure to be here. What I plan to do today is really to talk about three problems which are fairly elementary, kind of every undergraduate can have, which looks completely unrelated to each other. And I will present the problems, I will present their history. Two problems has been solved already, and one problem, I hope it will be solved eventually. Maybe some of you can help me or us with this. And kind of the idea I want to push is that maybe, or probably, or well, hopefully some of the methods which were developed in the other two problems, even though they look completely different, we can help to solve the third problem. So the way I'm going to do it today, I'm giving like 3 independent lectures about each problem separately. My original plan was not even to tell you anything about the connection, but because this talk is a double goal, is a first talk of Minerva, but on the other hand, it's a colloquium. I feel it maybe won't be fair for the people who came to the colloquium if they will hear only about the problem, not about connection. So I will here and there, I will give some hints that why they might be related. So the first problem, the first subject is the so-called Gromov overlapping. Gromov overlapping problem. And the story starts actually in the 80s. In the 80s, Borosh and Furedi, at that time, being undergraduate students in Budapest, proved the following beautiful results that respond to a theorem, to a question of Erdos. What they proved that for every set P in R2 of size n, there exists some point R square in the plane, which is covered by at least 2,9, well, to be more precise, minus little o of 1, n over 3 of the triangles determined by P. Right? Very simple theorem. You have n points in the plane. You draw all the possible triangles. There are n, choose 3. And the theorem says that doesn't matter what's the set, doesn't matter. There are 3 points. There are a point which is covered by 2/9 of them. By the way, this 2/9 is optimal. I made a mistake with it. Okay. Shortly after that, Barani proved the d-dimensional version of that, given for every P in R to the D. Now, D is any dimension. There exists some constant CD greater than 0, depending on D, such that for every P in RD, at least there exists Z in RD covered by at least CD and choose D plus 1 of the simplices determined by P. Okay, it's clear. You know, we are mathematician. We like to generalize. This is the natural generalization to the d-dimensional case. The theorem, what is exactly it's only in the case of d equal 2, the precise constant is known, and this is optimal. It's known that CD goes to 0 when d goes to infinity, and this is kind of a kind of theorem in the area of convexity and et cetera, et cetera. Okay, up to now, everything is that. Then Gromov came with the following, at least for me, amazing theorem, really amazing, because maybe I will draw, rather than writing the theorem, I will draw the theorem. The theorem of Gromov says, let's take first Borsch and Foredi theorem. Borsch-Foredi theorem says that, okay, you have n points in any way, you draw the triangles and they cover a point. Now, Gromov theorem says, take the n points and make the triangles not by straight line. Do it in any way you want. In any way you want, make them. Now you can do them very narrow. You know, I can take, for example, this one and this one, and then I can do this extremely narrow, right? In fact, if you do first the Borsch-Foredi theorem and you see a point Z which is covered by 2/9 of the points, you can completely bypass it. Make sure that you are not there. And Gromov tell you it won't help you. It's not there, but there is a point which is still covered by 2/9 of them. When I read it first time, we are among friends, so I can talk honestly. When I read first time, you know, Gromov is great, maybe the greatest. But, you know, when he writes things, he's not always careful that this, it looks like couldn't be true, because you can escape from the point and that, but I draw some pictures to myself, and then I realized, you see, if you really insist that all of them will be very narrow, so which means once you fix this line, you know, you cannot change this line. Now all the other triangles which are sitting on this line, you see, okay, if you want them to be very narrow, but like, for example, you know, you have this one, you want to make it very narrow, you have to also to do it something like that, right? So you will push it somewhere, and then the point will catch you. Okay? And then he proved a d-dimensional version of this theorem, and with a constant which is better than the constant which was known before for the CD. He proved there is a constant. Now, in a minute, I will formulate the results in a more precise way. In a constant which is better than what was known before. It's still a kind of a long-standing problem. What is the rate of CD? So you can define CD for the affine case that you are allowing to do this triangles or simplices only by affine map, and you can talk about topological CD. It's not known if they are the same or not. Anyway, the rate of growth is still an open problem. The rate of a decrease to 0, it's still an open problem. But Gromov contribution is not only by this amazing theorem, but also it kind of changed the way to think about this problem. Because I think that before Gromov, people thought of it as a property of the plane, as a property of the Euclidean space R to the D. It taught us to think of it as a problem of the simplicial complexes. So let me, because I want really to be kind of self-contained, let's recall what is a simplicial complex at X. What does it mean, a simplicial complex? with or on a set of vertices V. So it's the following is a collection. First, I'm very formal of subsets of V closed under inclusion. So, namely, if A is in the collection and B is a subset of A, then B is also in the inclusion. Let's say that V is finite today. I mean, I don't think we need more than that. And then this sometimes called the cells, right? The cells of the simplicial complex are all the subsets which are inside the collection. The dimension of sub A is simply equal to the size of A minus 1. So, you know, the dimension of a vertex is one point is 0. Dimension of 2 points, this is an edge. So the dimension is 1, etc. The dimension of X is the maximum of the dimension of A for all A in X, right? That's the dimension of the largest cell. And the X is called pure simplicial complex if all maximal, let's call this D from now on, the dimension of, and I will always assume that it's pure, all maximal cells are of the same dimension, so dimension D. By the way, computer scientists like to call it what we call pure simplicial complex. They like to call it a uniform hypergraph. It's essentially the same. They usually think only about those, but it doesn't really matter. The only good thing, if somebody talking about simplicial complex, then you understand that he learned mathematics as an undergraduate. If he talks about hypergraph, it means that he learned computer science. But they're essentially the same thing. And now, and now, but of course, this is the formal way. The right way to think about them is that this is a kind of a geometric or topological object, because we fill in the edges. We really think that we glue there a real edge, a segment, you know, in every triangles, we glue a triangles and we have a geometric object. And then what Gromov, the definition is, definition, let's say if epsilon is greater than 0, X simplicial, say, complex of dimension B, and then X is epsilon. There are two definitions here, geometric or topological, as the epsilon geometric topological overlapping property if for every f from V to R to the D, you know, I take a map from the vertices, I put n vertices in R to the D, and then I can extend it. If basically, if I extend it by affine way, there is a unique extension, right? I put a straight line, I put in the thing. But in a continuous way, there are uncountably many possibilities to extend it to continuous way. So if for every A, F and here, and any affine, so if affine or respectively, right? I'm just writing it like that, continuous extension from X to, maybe I'll call the extension F tilde, to RD, there exists Z in R to the D such that Z is covered by epsilon proportion of XD. I forgot to say that let's call the Xi here is all the cells in X of dimension I. Sorry, dimension of A equal I. I look at the top dimensional cells. I took the image of them, and I will say that the complex, now I think of it as a property of the complex. The complex as the epsilon overlapping property if epsilon proportion of the top cells covers some point. There exists a point which covered by them. Doesn't matter what is the map, etc. And now in this language, so Borsch, Foredi, or Barani, so let X, let's call it X be, I don't know, K, I don't know if there is a standard name for the K, Dn be the complete simplicial complex on n vertices of dimension D. So we take n points, we take all the subsets of size at most D plus 1. So this is a simplicial complex. And Barani theorem says, that K, that for fixed D, all K and D have some CD independent of N geometric overlapping. Right? This is just another way to formulate the theorem I said before. Right? That's clear. And Gromov says that fixed D, all K and D are even, of course, the stronger property, CD prime, topological overlapping. Okay? That's just a translation. Okay, now, well, I promised a little hint to what will come later. So let's check for a second the dimension 1 case of this story, which is kind of trivial. And here is just one little observation. Let's recall that a graph, I don't want to even to give a precise definition, because the notion of expander graphs is very well known, right? It's so well known that I'm afraid to talk about it when no guy is in the first row. And expander graphs are basically graphs such that if you cut them into two parts, there are many edges going from one side to another. Let me show you that expander graphs have that property, even the topological one. Why? Assume you have such a graph, and you take a map from that graph to R to the D, but this time D just equal 1, right? So I have a map from the vertices to R. So this means that I send the vertices somewhere to points on R. Okay. Now and then I extend it in a continuous way to the graph, to the edges of the graph, right? Then I have to prove there exists a point which is covered by many of them. Okay, let's take a point such that I don't know to count, but let's say that this point is more or less that half of the vertices above it and half of it are below it. Now, all the edges of the graph, which are, so this divides the vertices of the graph into two sets, those which are coming down here and those which are coming up here, right? All the edges between these two sets in any continuous map should pass through this point Z, right? So expanders have this topological property, have this overlapping topological property by what is called intermediate value theorem. That's all, right? So actually now I can tell you that nowadays we call simplicial complexes which have epsilon geometric overlapping, we call them geometric expanders, and those which are topological, we call them topological expanders. So this will come up. This is just an hint to where are we going to the I-dimensional expander. That will be something which will relate all our talks to each other in one way or another. Okay, so now after saying that, let's recall what is the theorem of Barani and Gromov. They said that the complete graphs, the complete simplicial complexes are geometric expander or topological, even topological expander. Amazing theorem, especially theorem of Gromov, really amazing theorem. But if you go to dimension 1 to prove that the complete graph is an expander is a triviality. This is an exercise for elementary school kids, right? The whole point of the theory of expander graph is to find families of graphs of bounded degree, which are expander, right? Which are the property of expander. So Gromov put forward the following questions. Gromov problem. Are there, given D, greater than 1, because for 1, these are existence of expanders, for example, right? Given D greater than 1, are there bounded infinitely many? Is there a family of D-dimensional bounded degree? Are there bounded degree geometric or topological expanders? Namely, can you find an infinite family of dimension D simplicial complexes of bounded degree? Bounded degree is simply every vertex is included. What is the degree of a vertex in a graph? The number of edges containing the graph. So bounded degree means that every vertex has only boundedly many cells containing it. It's the same as have only boundedly many edges. Okay. Okay. So this is much less trivial. Well, also existence of expander is not completely trivial. No, it's known for many years, so we think of it as trivial, but it's not really trivial. And then few years after that, Gromov did, well, I think it was published in 2010, but I think he was kind of around with this for maybe 10 years and lectures about it, etc. And then around 2013, I think, a joint paper of all the great names of the subject. So starting with I forgot, Gromov himself was one of them. Fox, Jacob Fox, Gromov, Laforgue. The name Laforgue will come again in my talks, but this is the younger brother. Then this is Vincent Laforgue. I will talk also about Laurent Laforgue, but not today. Well, actually, maybe, no, not today. Gromov, Laforgue, our Asaf Naor, and Janusz Pach. And they prove there exists bounded degree geometric expander. okay, for every D, geometric. They gave two proofs. In fact, they gave more than two proofs, but kind of two main direction of proof. The first proof is random, because my time is little limited. I think everyone will, if I let's think about dimension 2. If I will tell you, make a random two-dimensional simplicial complex of a bounded degree, probably we all come more or less with the same results. And anyway, so they show that random simplicial complexes are geometric expanders. But it's not so difficult to see that they are not topological expanders. So this is suddenly the I-dimensional case, and I will show it a number of times during my talk, that the I-dimensional, we are going to do generalization to I-dimensional, behave differently in some ways from one-dimensional. It's not like generalization from one dimension to I-dimension for the sake of generation. I-dimensional, I is not very high. I mean, 2 and up behave qualitative differently. They are not topological expander. And this was one proof. A second proof was using the so-called Ramanujan graph, complexes. Okay, so this is an hint of what we are going to do. The kind of the best type of expanders are Ramanujan graphs. I will talk about it next week. So next week, my talk will be about expanders in general. That will be, I will not talk about any new results next week, but some kind of an old results, but I will present the old topic of expander graph from a perspective, maybe not the standard perspective, which will maybe a combinatorialist will present them, but somehow in a way that will help me to go to the higher dimensional. And I was very happy to learn that Peter will not be here next week, because we always argue what's the right way to talk about this. So I will be able to do my own way without being attacked by him. Anyway, so you see that there is, we are coming through number theory. Number theory automorphic forms will come into the game later on, representation theory, etc. So this problem was solved. But it took several more years to do the topological. In fact, when I was talking with Gromov, he was not even sure of whether topological exists, whether they exist or not. Eventually, it was done. The first only in dimension 2 theorem. The theorem is eventually for every D. There exists also now I can talk about, right? I can talk about topological expander, bounded degree, topological expanders. This was done for D equal to, this was done by, in a joint work of David Kashdan, Tali Kaufman, and myself. And for every D, it was done by my student, Shai Evra. I think many of you should know him because he spent a few years as a postdoc, and he probably got a position because this is a great theorem with Tali Kaufman, and this is for every D. Now, what was the proof? I'll just give an hint and I'll stop here. You remember random doesn't work. Ramanujan complexes, you may suggest, Ramanujan complexes of dimension D are a topological expander. This is still an open problem. The trick which we implemented first here and then they generalized here was to take one dimension up. So the story is more or less the same, more or less the following. Ramanujan complexes, I'm cheating here about some technical details. Ramanujan complexes of dimension D plus 1, we don't know if they are D plus 1 a topological expander. But if you take the d-skeleton of them, kind of ignore the top, and decide to look only on the one level less, then they are d-dimensional topological expanders. This is because of the method of the proof. The method of proof is kind of built on the original method of Gromov. When I'll talk about that, I will say more. So the plan is the following. So in this series of talk, the next two talks will be one about expanders. The one after will be about a I-dimensional expander. This will be kind of preparation for the last three talks. The last three talks will be on each of the problems, extension of each of the problem I'm talking today. So then I will explain more about how this was solved. I just have to warn you, but I plan to explain everything from the beginning. It involved cohomology over the finite field of order 2 in a pretty amazing way. And I will not, and that takes us now to the second problem, which again, on the face of it, so now I basically now start a new talk. And the new talk, yeah.
For the geometric thing, if you just take the Ramanujan graph and you take his edges, the path, just path of length k, this is a geometric thing.
This is geometric, right? That's one of the proofs that of Asaf and right. They have, I think Asaf at the time told me that they maybe have 8 proofs, and eventually they put 3 in the paper, or 2 or 3, something like that. Anyway, this was great for me that they put the Ramanujan complexes, because I'll tell you in the next talk, I'll talk about it, because that's caused me, I knew anything about I knew nothing about this subject. Somebody told me, look, these 5 great people are quoting your paper, you should look at that, and then I learned.
The construction is logo mentioned stuff, but I'm not sure about that.
No. I can tell you after that. I don't want to go to that. You can think. No, Asaf, I think about it. A random 2-dimensional looks essentially like a graph. Yeah. I'm not showing the random that you used. The random that you used, I think they're not. Maybe there is another notion of them. Yeah, I should be more careful. Yeah. Okay, so now I'm going to the second lecture because I spent too much time on the first. And the second lecture is about locally testable codes, error correcting codes in computer science. Now, this is a problem which is even simpler to explain. And I think, so I hope the second talk will be shorter. It will be about locally testable codes. So what is a code? A code, error correcting code, you want to send information, you want to send bits, sequence of bits of length k. Instead of sending k bits, you send n bits. N is larger than k. And what you want is that if there are mistakes, you can repair them. Okay, we are mathematicians. We care about, we're not engineer, about the case n going to infinity, etc. So for us, we just define C code, or maybe the standard notation C is n k D code I will talk about what's called linear code, is a subspace, a linear subspace of F2 to the n of dimension k, okay, and distance d. What does it mean, a distance? So d is equal to the minimum of the Hamming distance. Hamming distance between any two vectors, alpha and beta, in the code which are not equal. Hamming distance is simply in how many bits they are different than each other. And now it's clear that when you send the code, when you have a code, you want the distance between the vectors in the n-dimensional space to be as large as possible, because if the distance is at least d, if you have d over two mistakes, you can correct them to the closest correct vector, right? Of course, to correct them, it's easier to say than to do, but I'm now ignoring this aspect of the theory. And it was, I think, going back to Shannon, who really started all this, the mathematical theory of coding, that he was interested in infinite. When we say code, we always mean infinite family of codes, you know, that n going to infinity. And so C is good, some people say asymptotically good, if K over n and D over n are both more than some constant epsilon. You know, there are numbers, each one of the number between 0 to 1, and the family of code is called good if the K and D both grows linearly with n. And now it's not completely trivial that good code exists, but again, what happened there? Shannon, first of all, proved that random codes, whatever you mean by that, are good. And later, this was done 70 years ago, you know, it was actually at the same time of when Erdos did the random graph, more or less. I'm not sure if one influenced the other, and if so, in what direction. But anyway, it probably was, I don't know how you say in German, there is something, what is it called? Right, yeah, the spirit of the time was to do things like that. Anyway, they are good codes, and ever since then, the theory of error-correcting code flourishing with a lot. I'm kind of jumping to the modern theory, and the code C is locally testable if if there exists an algorithm, a random necessarily, algorithm which reads only a small amount of the bits. You know, you are getting 2,000. Nowadays, really, people are talking about codes such that n is 200,000. You are getting such a huge a sequence of bits, and the receiver, if the number of mistakes is at most 5%, then he has an algorithm to correct it. But if there are 40%, can do nothing. So it doesn't want to read all of them and then to discover that this is rubbish, completely corrupted. But then, so you want to read only few of them. The best, we hope, is to read only a bounded number of bits, independent of n, such that a random, which maybe I'll go right away to the most, I mean, over the years, people demanded maybe less, and then eventually more and more, which reads only, say, q bits. In the language I write q, they call it queries. You are allowed to ask only very few questions, q bits out of n, and decide, well, with high probability, if the vector is in the code, or at least very close to it, or close to it. So when I get back to this problem in details, I'll give a precise definition, and the code, namely in the subspace, or close to it, or at least close to it. Okay, so I think it's kind of understood. Now, this was one of the major problem, if not the major problem in this area. Why this was so difficult? In fact, the prediction of the expert in the area, there was a good number of experts conjecture that it's impossible, which it looks, it looks quite impossible. I read only 70 bits out of 2 million, and I can tell you if the vector is good or not. It looks like crazy. And there was a large group of people who conjectured that this is possible. And interestingly enough, there was an intersection between these two groups. There was one of the big experts who conjectured one side and then changed his mind to the other. Oh, I'm sorry. Oh, you are sorry. I'm sorry. I missed the main point. There are good, there are testable codes. That's not so difficult to find testable code, but then they're not good. Among the good, can you? Okay, so I'm sorry. I forgot. Thank you. Thank you. I'm sorry. I'm nervous because of the time. So I'm what? The CQ problem, right? Right. So the question is: are there codes which are good and locally testable with a finite number, with a bounded number of queries together? Over the years, people had not good. There are, like the Adamar code is a fantastic for local testability, but it's very poor on the rate. There are Reed Solomon. They are, I think, also good that, but not good. They are locally testable, but not good, etc., etc. The problem was, can you achieve all these properties together? So, it got the name, the C cube, the nickname, the C cube problem. I'm sorry. Yeah, that's the real difficult problem. Are there codes which are good, namely with, why this is called C cube, with constant rate in the means K over 2. That's the rate of the code. K over N, sorry. Constant distance, they usually, they talk about the normalized distance. Constant distance, which means D over N. And constant number of queries, absolute constant. So this was the C cube, the nickname of the problem was the C cube problem. Now, why people were suspicious that this could not exist? First of all, it looks like a little bit contradicting, but also the theory of codes, usually not on every aspect of it, kind of follow up the random codes. Kind of the common wisdom is random codes are the best, right? And the random codes are known not to be locally testable. So here is a fact. Random, so you feel like little connection with the previous. Random codes are not LTC. So, usually you say that it's very difficult to, if you know in mathematics, in this area of combinatorics, many times you prove first that random objects satisfy the property. It's still, and can be highly non-trivial to find explicit example, right? It's like to look for an explicit example. Now, if you to prove that, the sentence said that to prove if the random satisfies and then to find an example is to look for a hay in a stack of hay. But if it's if the random does not satisfy it, it's like looking for a needle in a stack of hay, and even the needle does not exist, maybe. See, so that's why this problem is, and the answer is Well, the good news is indeed they exist. And kind of part of the amazing of this story is the timing, the theorem, and this is a joint work of the same Evra that was mentioned before. Sorry, you read Binur first. D, Evra, Livne, Ron Livne, Lubotzky, the same Lubotzky was mentioned before, and Moses. But what is amazing, at the same week, this was major open problem for 30 years, and the same week on the archive, 2 papers are found, and the other one by Pan Teliv. For some reason, it always appears P before, like that, and Kal Shev, both from Moscow, and both works prove that there exists good locally testable code. Actually, it's interesting, Panteliv and Kalshev came from a completely different community. They were interested in a different problem. When I'll get back to this problem, I will tell you about it a little bit about quantum codes. They really work on quantum code. They solve a major open problem in that area, finding LDPC good quantum code. That's not so difficult to what is it? And they deduce from their solution, they deduce LTC codes. We came from a different direction, but somehow in our story, high-dimensional expanders appear also here. So now, in the last 10 minutes, I'm going to give my third talk. And the third talk will be about sofic and non-sophic groups. So again, the problem is easy to explain to every second-year undergraduate student, but it became a major problem in group theory. So sofic and non-sophic groups. So let's gamma be let's talk all the time that gamma say generated by S, a finitely generated group. I mean, it's not only about finitely generated, but it can easily reduce to finitely generated. So let me work with finitely group. So gamma is called residually finite. A group is called residually finite if it can be separated, the point can be separated by finite quotients, namely so for every, say, x, y in gamma, there exists a finite group F and homomorphism from gamma to F such that rho of X is not equal to rho of Y. It's clear to see that it's the same as enough to show that for every non-identity element, there exists an homomorphism that which goes to a non-zero. So you can separate the points equivalently for every X not 1 in gamma, there exists rho from gamma to F with rho X not identity. Good. Now we all remember what? Not identity. So thank you. We all remember the Cayley theorem. The Cayley theorem, which says every finite group can be embedded into the symmetric group, to some symmetric group, every group, but the symmetric group N. In fact, it's really the symmetric group on the set F. Right? The group acts on itself by multiplication from the left, and you embed it. So I could formulate that every that every finite, that a group is residually finite if it can be separated by homomorphism to the symmetric groups. That's the same thing. But we get even more. We get, note that we get a little bit more, that we get gamma residually finite means, if and only if you want, for every x not 1 in gamma, there exists, you see what I can start to do the following. I separate, I take gamma and I will start to take a normal subgroup 1 which separates some point. Then I take another subgroup which separates another point. But I can assume that they are really a sequence which going down, right? There is a normal subgroups going down to the identity of finite index subgroups. That's equivalent. So, and I can, so if at the moment I separate x by this one, then I want to separate another one, y, then this one will separate both of them, right? From 1. So if you think about it now, if by this way, when f acts on itself, right, x acts on itself without a fixed point, right? So I can now formulate it like that. A gamma is residually finite if and only for every, no, I can say the following, maybe that's better. Residually finite if there exists, well, Ni, and sequence of homomorphism rho I from gamma to the symmetric group on Ni. You know, the first is a symmetric group on that side. The second symmetric group on a larger and larger set, such that we have two conditions. If rho, if x is not 1, then rho Ni, then the distance, I'll explain in a minute what I mean by that, of rho Ni of x from the identity of the symmetric group Ni is equal to 1 for every Ni large enough, right? Because once in this type of separation, once I separate the point, it has no fixed point. Now, what is the distance between two permutations? The distance between two permutations means on how many points they do not agree, right? This one fixes them all. This one eventually does not fix anything, right? So the distance between them is equal to 1. You're right. Okay, the distance is the proportion. Okay, the distance is not the Hamming distance, it's the normalized Hamming distance, the proportion of the number which they are different than each other. Thank you. Okay, so that's one condition. And the second condition, which is the trivial one, of course, that rho, the distance of rho Ni of the identity from the identity is 0. It's always go to the identity, right? That's trivial. Now I want to define what is a sofic group. A sofic group, this definition go back to Gromov and well, and Benji Weiss. I can tell you a little bit about the history, and when I get back to this talk, I will tell you where the name came from. This is a secret. I will reveal the secret to you. They say that gamma, so gamma is called sofic. Okay, that should be it. Gamma is sofic if there exists maps, not homomorphism, maps, rho Ni from gamma to the symmetric group on Ni point, such that if x is not 1, then the lim when ni goes to infinity of the distance between this is 1. Oh, I forgot to say. No. I try to save time and then I'm doing a bad job. So let me. Sorry, there exist maps that satisfy condition 0. They are not necessarily homomorphism, but they are kind of asymptotically homomorphism. Namely, for every x and y in gamma, the distance, the normalized distance, right, between rho ni of x, y, and rho ni of x time rho ni of y. If this was an homomorphism, then the distance should be 0. So we are only requiring that when I goes to infinity, this is equal to 0. So they are almost homomorphism. The maps are not necessarily homomorphism, but for every x and y, they eventually very close to be homomorphism. The second condition will be that if x is not y, then it's separated from the identity. And here, the identity does not have to go to the identity, but yeah, anyway, you can send it to the identity. It doesn't matter because they're not homomorphism, then it will be 1. So a formal, I would say the following. Reasonably finite group is group that can be separated by homomorphism to the symmetric group. Maps which satisfy this condition are called almost homomorphism. So it can be separated by almost homomorphism. So of course, every reasonably finite is sofic, but also this was the big thing which make if you know, I don't have time to define, but if you know what is an amenable group, every amenable group is sofic. Now, amenable int for the future is the opposite than expander. Amenable are such groups that you can find inside them subsets which are not pushed out by the generators. But if you have a set F inside gamma so that the boundary of it is small, think of gamma as acting on the set. So think of it as acting on the set. This action is not well defined, right? Because it sends the points on the boundary outside, so it doesn't act. Never mind, just change, do with them whatever you want. And most of the elements in F, it acts nicely. So these are exactly almost homomorphisms. So if you take this F to be bigger and bigger and bigger, then you get almost homomorphism which separate the points of the group. When I come back to that, that will be the last talk on the series. I will explain it a little bit more. And then now, okay, so reasonably finite, amenable. Over there, people start to think maybe all groups are sofic. Now, at the beginning, it was not such an important problem. But over the years, many theorems, old conjectures, which were posed even in the 40s or the 50s for all groups, were proved for sofic groups. Now it's important. If every group is sofic, then the problem is solved. But to be honest, once the sofic groups became such a successful story, people stop to believe that every group is sofic. It looks too good to be true. Even though I have maybe 1 minute or maybe minus 1 minute, I'll give you a very simple example. Kaplansky, one of Kaplansky conjectures, such a trivial statement would ask in the 40s. Let gamma be a group. Let K be any field. Look at the group ring K gamma. So you know what the group ring is, just the finite formal expression of gamma with cube, and you multiply it. He asked the following: is it true the following? If say alpha and beta are two elements in Kf, in K gamma, such that alpha times beta equal 1, is it true that is it necessarily true that beta times alpha is also equal to 1? That's all. If you think about it, it's a kind of a combinatorial problem that you play a role. But it turns out to be a highly non-trivial problem. In fact, for characteristic 0, it is true using the theory of von Neumann algebras. But the characteristic, positive characteristic, it's still open. And Elek and Jabbo proved some years ago, I don't know, 15 years ago or so, that it's also true in characteristic P for sofic groups. Okay, so such is algebra experiment. So the question whether all groups are sofic is maybe one of the most outstanding problem in modern group theory. Now, unlike the two other problems that we know to solve, we don't know to solve. But there is a feeling that maybe we are getting close, and we have now a methodology. In fact, I'm writing now some papers with Michael Chapman, who is here, and that we feel that maybe we are almost there. But you know, in mathematics, 99% of a proof. What?
Yes or no?
Of course not. Nobody believes that, but we feel, you know, many people suggest take a simple group, take Igman group, take the Burger-Moses simple groups. You know, many people suggest they cannot be sofic. Even Berenstain group, they are not residually finite. There is a feeling that they are not sofic, but there is no method. What I will try to explain in the talks, if you will be patient to stay till the end, because I will not talk about it till the last talk, but we'll develop some machinery that we will implement it for the other talks, which will be, you remember, I don't want to frighten you, but I'm going to do some very elementary cohomology over F2, which is extremely elementary linear algebra. I will explain everything from start. But to solve this problem, basically, we need to prove the same theorem that was proved over F2 for solving the Gromov problem. We will have to solve it instead of coefficients in F2, in coefficients in the symmetric groups. So it's kind of a non-commutative cohomology, but we'll have to solve it only in dimension 1, which is much easier usually. On the other hand, a non-commutative is much more difficult. So we got stuck. Yotam is here, and Dickstein and Iridinur solved the problem in a different metric on the symmetric group. So it's kind of encouraging that we are almost there, but so far we didn't manage. I hope this one of the smart young people, I don't expect the old one. Peter, it's including you to help, but the young people, I hope, will maybe able to, we have a feeling that we are maybe almost there, but so far we don't have it. So that's all what I have to tell for today.